अभी लाइव नहीं हुआ था ना। ये गलत है इसे।
हाँ तो ऐसा रहेगा।
हाँ
ऐसा तो लिखना। फिर कैसे चेक करो?
ये इधर आ गया।
ओके ना।
एडमिट करो
ना वहीं से एडमिट नहीं आता
तो फिर ये क्यों आ रहा है?
यहाँ हैप्पी डेव कंट्रोल कर रहे हैं ना।
और ग्रेड करना
कबूतर कबूतर आ रहा है।
फिर कैमरा क्यों दिया है उधर?
हम कहाँ लिए कैमरा? ये तो जो लेबर आए हुए उसी को तो प्ले कर रहे हैं ना।
कोई आया देखो वही किधर कर रहे हैं?
यहाँ टू करके मैसेज आएगा ना, साउंड आएगा ना। नहीं आ गया, वहाँ आया जो हैप्पी डेव कंट्रोल कर रहे हैं।
अच्छा यहाँ पे मैं लिखता गुरु नहीं हो रहा हूँ कि चैट ज्वाइन दे चैट 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 अभी नहीं ऑन किया ना। हट साला कहाँ चला गया? मुझे लगा यूट्यूब चैट यहाँ से ही करना पड़ेगा हमें। यहाँ से यूट्यूब है ना, यूट्यूब में जाओ ना थोड़ा। लाइव चैट करो बाद में करूँगा, बट वहाँ से अलाउ नहीं करेंगे, मैं लिख नहीं पाऊँगा। ये तो लाइव सेशन इसको पहले कर लो।
टाइम जाएगा। खुशी
देखो वहाँ पे कोई खुश कर रहा है।
ये तो हैप्पी डेव जो ये स्क्रीन दिख रहा है ना, ये हैप्पी डेव का ट्रेल कर रहा है ना।
बट ये नहीं दिखाना चाहिए ना।
ना पर क्या दिखाएंगे फिर अभी?
वो जो पहले वाला आ रहा था
लोग, हाँ वो दिखाना चाहिए थे इसे।
तो मुझे बोला था वो वाला दिखा कर आएगा, बट नहीं आ रहा। तुम लोग देख नहीं पा रहे, वहाँ से यही दिखा रहा है।
यही तो दिखा, ये तो मैं देख पा रहा हूँ, मतलब सब देख पा रहे हैं ना। मैं तो बाहर से खोला है, जैसे आपको खोले वो तो बाहर से, यही तो है कंट्रोलर हमारा। हम जो ये देख रहे हैं ये सब देख रहे हैं।
रिकॉर्डिंग स्टार्ट हो गया।
स्टार्ट कर दिया।
यूट्यूब है। इतना लोग हंसने से मुश्किल है, बातें करने नहीं दे
ना दिखा था, कोई बोल नहीं पाएगा, कोई क्वेश्चन नहीं तो भी टाइप करना पड़ेगा।
चलो चलो चलो
लॉग में हो मीन्स बट मैं क्यों नहीं पा रहा हूँ? तुम लिख रहे हो? मैं तो नहीं लिख रहा हूँ।
आपको ये लॉगइन है लेकिन 6 समथिंग आपका ये लॉगिन ही नहीं है। मेरा जैसे अनिश राय आ रहा है ना लॉगिन, जीमेल से लॉगिन है ये।
मेरा भी तो है।
ना आपका लॉगिन नहीं है।
नींद टूटा है।
मैं आपके समय से लॉगिन लॉगिन है, मुझे समझ नहीं आ रहा है।
मैं एक ही अकाउंट से कर रहा हूँ शायद इसीलिए।
ना देखिए अकाउंट से क्या करें?
तुम लिख पा रहे हो? गुड मॉर्निंग लिखो।
लिख कर
गुड मॉर्निंग ऑल।
यहाँ लिख रहा हूँ तो मतलब जा रहा है ना लिखा नहीं कोई और है। डीपी तक था अभी बंद किया।
तो ये हमारे से नहीं होता है
ना
अलाउ नहीं है।
उनको करना पड़ता है।
श्योर ना हमें होता है
पता है तो फिर रिक्वेस्ट में बोला काटो सब
ये क्या बोल रहा हूँ वो शायद हम बनाने के टाइम वो तो देना पड़ेगा जी क्या आगे होना चाहिए लाइव होना ना एक तुम कर रहे थे
ना
शायद।
ये
ना ना तुम अभी ऐसे किया ना उसने लेट में ले रहा ना यूट्यूब में।
ना ना इतना नहीं किया देखना चौकसी
तो गुड मॉर्निंग लिख रहे हैं सब, मैं क्यों नहीं लिख पा रहा हूँ?
हाँ ये हम कर रहे हैं
हैं?
हम ही कर रहे हैं
हैं?
हम ही कर रहे हैं
इसीलिए मैं बोल रहा हूँ उसको प्रेजेंट करो बोला
क्या प्रेजेंट
हमारे से। नहीं ये तो बाहर सब ही हो रहा हो देखो ये तुम नहीं कर रहे हो
ना ना
ये भी तो कर रहा तो
ना
देखा रहे
मैं ही कर रहा हूँ थोड़ा लेट से कर रहा है देखा उनको साथ आएगा थोड़ी देर
प्रेजेंट कैसे करो नहीं
ये क्या प्रेजेंट
वो जो यूनाइटेड लोगो आया था वो लोगो कैसे एकदम फास्ट वाला जो था ना ये वाला तो हम नहीं करो
ना हम तो कर
हम करो देर में दिखा रहे हैं भाई
यूट्यूब में
अभी आएगा देखो ना
आएगा कंफर्म आएगा
मैं जो देख करूँगा वो आएगा ना
थोड़ी देर में आएगा थोड़ा टाइम में
हम करो कैमरा बंद क्यों नहीं किया
बोलो
लोग देख नहीं पा रहा हम लोग क्या कर रहे हैं
ना वो यूट्यूब खोलना
है ना
इसमें भी तो दिखाई देना चाहिए
गूगल मीट में भी तो होना चाहिए
ना
ना
गूगल मीट शायद यूट्यूब शायद हम कंट्रोल करते हैं गूगल मीट नहीं ये तो क्योंकि यूट्यूब में हम जैसे गेम वैसा है ना तो गूगल
अच्छा अच्छा सही बोला
ये पता नहीं क्या लिखा और एक टेंशन जानो यार कोথায়
यूट्यूब में तो कोई आया भी नहीं ज़्यादा ना हैं बट वो वाला दिखाई दे रहा है ना हेट वो वाला प्रेजेंट क्यों नहीं कर पा रहा हूँ
कौन सा प्रेजेंट
वो पहले वाला जो आया था
क्या स्टार्ट नहीं कर रहे सभी एटी एक्टर
है नहीं वो वाला जो भी बनना चाहता हूँ प्रेजेंट करने से तुम्हारे ये हमारी स्क्रीन दिखाई देगा और वो लोग कुछ देख भी नहीं पाए ना यूट्यूब से।
ना वो यूट्यूब पर नहीं, मैंने कौन कर गया तो
हैप्पी तो नहीं कर रहा, हम ही कर रहे हैं सब।
ना वो शायद गूगल मीट देख रहे हैं या फिर वो मुझे पता नहीं कौन क्या देख रहा है।
बट यही करेंगे ना, हम क्या करेंगे वैसे, और तो ही नहीं मेरा ऑप्शन है। गूगल मीट में यही दिखाई दे रहा है
ना, गूगल मीट में तो ये दिखाई दे रहा है ना, इसीलिए तो बोल रहा हूँ गूगल मीट कोई और कंट्रोल कर रहा है।
इधर बता बोलते। हाँ इधर चैट बॉक्स है। अच्छा अच्छा अच्छा, हाँ हाँ यूट्यूब चैट बॉक्स था तो ओहो हाँ 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 हाँ, কিন্তু এখানে তো বোঝা যাচ্ছে না, দাঁড়াও 1 মিনিট। ঠিক আছে, এখন মনে আর আসবে না, বন্ধ করে দিয়েছি। ঠিক আছে ঠিক আছে, হুম তাও তো আসছে আবার, এই আওয়াজটা অন্য আওয়াজ মনে হয়। अभी तो फ़ोन किया तो जो आवाज़ आ रहा है ना, टंग टंग करके आ रहा था, वो बोले कि बंद कर दो, बट कहाँ से बंद करूँ?
कहाँ से करते हैं पूछा नहीं, फिर कहाँ से करते हैं?
उसको भी कैसे पता, हम कंट्रोल करें, उसके हाथ में है देखिए वाला। वाला कैसे बंद करें?
क्या प्रेस किए फिर?
ये तो हटने में आएगा, कोई प्रेजेंटेशन भी देगा फिर भी टाउन टाउन करेगा। नहीं तो ये बंद करने से तो मैसेज बंद होगा।
बोलिए तो कहाँ से करते हैं?
हाँ बिदा, আমার ওডিও তো অফই আছে,
इसमें होगा शायद।
ওটা অন্য কিছু সাউন্ড, টক টক আওয়াজ আসছে তো, ওটা তো কোই লোক জয়েন করছে তখন সেটা আওয়াজ, যখন ঢুকছে তখন। এখন শোনা যাচ্ছে?
काटते क्या कहाँ से?
আমাদের তো বন্ধ, এটা আমার আওয়াজ না, আমাদেরটা অন নেই, কিন্তু যখন আসছে তখন ওই টক টক আওয়াজটা আসবেই তো, আমি দেখছি ওটা মনে হয় অন্য কোনো। আচ্ছা আচ্ছা, আর ওইটা প্রেজেন্ট করো, যেটা লোগোটা প্রেজেন্ট করো, এখন তো পুরো দেখা যায়, আগে যেমন প্রেজেন্ট ছিল না ওখান থেকে প্রেজেন্ট করছিলে। না না, এখন ওই ইয়েটা, ওই যেটা ছবিটা, যেটা ওই স্পিকার দিয়ে ছবি দিয়ে প্রথম ছিল না, ওইটা থাকলে ভালো হয় না? আচ্ছা আচ্ছা ঠিক আছে, না বলি অনেক তোমাদের ওই ছবিগুলো দেখাচ্ছে না, ক্যামেরা অন করা আছে, তোমরা যা করছো সব দেখতে পাচ্ছ না ইউটিউবে। না হ্যাঁ এখন অফ হয়েছে, হ্যাঁ ঠিক আছে, ঠিক আছে। पूरा हमारा आवाज आ रहा है, और अच्छे बाद में नहीं नहीं आवा तुम्हारे आवाज नहीं, वो ऑफ किया, अब हैप्पी ऑफ किया, वो छोड़ो,
अनपिन नहीं करो।
ना ना
क्यों?
ना रहना दो।
अरे ये ना अनपिन तो
ना ना वो हैप्पी था ये, ना वो किया
है, ठीक है तो हम क्या करें?
तो करो, फिर ये करो। कोई नहीं दिखाई दे रहा है यूट्यूब में, थोड़ा लेट में आता है।
थोड़ा सा
অনিন্দ স্যার কি বলেন? হ্যাঁ স্যার, হ্যাঁ স্যার, হ্যাঁ হ্যাঁ স্যার, আমাদেরগুলো মিট করাই আছে স্যার। ওই বাইরের থেকে যারা ইয়ে হচ্ছে ওইগুলো একটু ঝামেলা হচ্ছে তো। কই না তো, এখন তো আমাদেরটা বন্ধ করা আছে স্যার। হ্যাঁ, হুম হুম হুম। আমার আপনি শুনে দিন। হ্যাঁ শুনে, হ্যাঁ শুনে দিন। হ্যাঁ तो फिर तुम्हारा यहाँ पे सुनाई देगा तो मैं अगर बात करूँगा तो। फिर तुम्हारा यहाँ पे सुनाई देगा तो मैं अगर बात करूँगा। तुम्हारा यहाँ पे सुनाई देगा तो मैं अगर बात करूँगा।
तुम्हारे सबके काम की चीज है, जो चीजें हमारे जनरल काम की है।
Good morning, everybody. On behalf of the Department of Physics, National Institute of Technology, Sikkim, I would like to welcome you all to the inaugural session of the Faculty Development Program on Quantum Information and Computation. Quantum information and computation is one of the most important areas of research in the present age. The subject stands at the crossroads of physics, computer science, and mathematics. The workshop aims to provide students, teachers, and researchers working in diverse fields of physics, computer science, mathematics, and other engineering disciplines an introduction to various topics in the field of quantum information and computation, both theoretical and experimental. The discourse has been conceived to be at the level of the theoretical minimum for the chosen topics. We will begin with today's keynote address, where Professor Aditi Sende from Harish Chandra Research Institute, Prayagraj, will give an overview of the subject. We will have lectures on quantum mechanics, foundations of quantum information, quantum entanglement, quantum communication, quantum cryptography, open quantum systems, quantum error correction, quantum computation, and experimental realizations of quantum computer using NMR, ultra-cold gases, and superconducting circuits. The purpose of the workshop is to provide the participants an idea about the wide scope of the field of quantum information and computation. In this COVID-19 pandemic scenario, we have been forced to adapt to virtual mode of communication. However, the online workshop has enabled us to reach a much larger audience for this workshop. We thank the participants and especially the speakers who have taken time out of their busy schedules to deliver lectures in this workshop. We hope that the workshop turns out to be beneficial for the audience. Thank you. Now I would request the Honorable Director of NIT Sikkim, Professor M.C. Gobil, who is also the Chief Patron of the workshop, to say a few words. Good morning, all of you, faculty members, staff, dear students, the guest participants, the esteemed speaker in the workshop. It is my pleasure and privilege to host this faculty development program organized by the Department of Physics at NIT Sikkim on quantum information and computation. As it has been already said by the coordinator of the workshop, quantum computing is becoming a hot topic for the future, and therefore we decided to organize this workshop for the benefit of, as said, for the students especially and for other participants also. I believe that it would be very beneficial for the final year as well as third year, especially computer science and electronics. And I appeal all the students, they must attend this workshop. Of course, it's good for the electrical students also, so they may also get the benefit because you must know about the future technologies. So as said, the quantum mechanics was developed during 1920 to 1930 by some of the greatest physicians who have ever lived. It is non-intuitive and even the practitioners of the theory often find it difficult to perceive the consequences. Albert Einstein dismissed quantum entanglement, a consequence of quantum theory, as spooky action at a distance. Einstein's view of quantum mechanics has been falsified by experiments over the last century. The application of quantum theory has helped us in understanding the universe that we live in. There are real-world applications of quantum mechanics as well in the form of ultra-precise clocks, uncrackable codes using quantum key distribution, emerging technology of quantum computers, entanglements, enhanced microscopy, and quantum biology. The present century has witnessed a revolution in harnessing the principles of quantum theory for information processing. The frontier area of quantum information science is truly an interdisciplinary one that is developed by scientists from physics, computer science, mathematics, and information theory, and others also. Some of the important developments were the discovery of quantum computers, fast quantum algorithms, quantum teleportation, super dense coding, quantum cryptography, and several quantum communication protocols. Quantum information science and technology promises to revolutionize the future computation and communication systems, which will ultimately have huge impact on the nation and our society as a whole. The government of India has prioritized this area of research through its Department of Science and Technology. It focused on the area of quantum information technologies with photonic devices, solid phase devices, nitrogen vacancy, magnetic resonance, ion trap, and optical lattice devices, superconducting qubit devices, and quantum dot devices. It has also focused on the mathematical and fundamental aspect of quantum computation and quantum information. NIT Sikkim aspires to play its vital role in the progress of the field of quantum information science. It is pertinent to note that there has been tremendous progress in the development of quantum computers in the past few years. IBM, Google, eBay, Honeywell are some of the companies engaged in this domain. In their Nature article published last year, Google announced that their 53-qubit quantum computer using their Synchromore processor has achieved quantum supremacy. The promise of quantum computers is that certain computational tasks might be executed exponentially faster on a quantum processor than on a classical processor. Their processor using programmable supercomputing qubits take about 200 seconds to sample one instance of the quantum circuit a million times. The equivalent task for a state-of-art classical supercomputer would take approximately 10,000 years. IBM disputed this claim and stated that tasks could be performed on their classical supercomputer within 2 days. In any case, it appears that quantum supremacy has indeed been achieved and the gap between classical and quantum computers is likely to widen in the forthcoming years. Researchers who are experts in their domain will disseminate their knowledge during the next 12 days in this faculty development program, which is likely to reach many interested learners through various online platforms. I wish the workshop a great success and once again appeal to take the advantage of this state-of-art topic and I think the future technology to all my students and the faculty members from the engineering departments, especially computer science, electronics and electrical engineering. And I believe that they will attend this workshop and will get benefited because we have requested all the learned speakers that they should concentrate more on the fundamentals so that the student can learn the basics behind the quantum computing theory as well as the information theory and how they can really use this quantum theory in practice. That is the most important aspect of this workshop, and I believe this will be going to achieve its goal and will be very, very beneficial. Once again, I thank all the participants who have really shown their interest and the students as well as faculty. Thank you. Thank you, sir. Our speaker for today's morning session is Professor Aditi Sende, who is a physicist working at the Harishchandra Research Institute, Prayagraj. Her research interests include quantum communication, detection and quantification of quantum correlations, interface of many-body physics with quantum information science, etc. She completed her MSc in Applied Mathematics from University of Calcutta and a PhD from University of Gdansk, Poland. She has been a Ramanikahal Fellow at IFPO, the Institute of Photonic Sciences, Spain, and Alexander von Humboldt Fellow at the University of Hanover, Germany. She has also served as Assistant Professor at the School of Physical Sciences, Jawaharlal Nehru University, India. She is a recipient of the Shanti Swarup Bhatnagar Prize in Physical Sciences in 2018 and the Bhuti Foundation Award for Excellence in Theoretical Physics in 2012. Professor Sende, please.
Thank you very much, Arvind, and thank you for inviting me in this nice workshop. It's a great privilege to be a part of this workshop. Of course, I will be delighted to come to Ravangla and attend this meeting, but I hope that can happen in near future. But in this pandemic situations, you have arranged such a nice workshop. I'm really looking forward to other talks and so on. So maybe I share the screen.
Ma'am, I'm interrupting you in between. We are very delighted to have you here, and I'm thankful for accepting our invitation, and will definitely invite you to the Sikkim. Definitely for the event in Sikkim and for me also. So thanks once again.
Yeah, thank you. Thank you for the invitation. Yeah, I will look forward for that.
Definitely, once this pandemic is little bit over, because we are also patterned enough, and we don't know that the travel is really risky nowadays. So definitely.
Okay, so I shared the screen. See my screen?
Yes, we can see your screen.
Okay, thank you. Okay, so as Aninder has mentioned, I will give an overview of the subject as well as the research going on. So I will talk about technologies, but I will talk about quantum version of the technologies. Now this actually lead to a subject which is quantum information and computation, as mentioned by Aninder, that it is in a crossroad of different fields, physics, mathematics, computer science. So I will try to give in now next 1.5 or 2 hours the overview of this subject. The question that I want to ask is the following: why do you want to build quantum technologies? Now, to answer this question, actually I will show you that you can also get answer, or you have to address certain questions which answer the fundamental issues, or which address fundamental issues in quantum mechanics or in other fields. So the technologies that I will talk about mainly are the computer, which we know, and probably in these pandemic situations we realize the importance of computer as well as communication devices. So I will talk about both this. Now, in communication devices can be broadly classified into 2 categories. One is communication without security. Without security means that this communication doesn't require any lock and key system. There is another category of communication devices that we want to build, is a secure communication, in other words cryptography, where actually information is locked and few people have the key who can open the lock and can gather the information. I will talk about the secure communication as well as communication without security in detail in later part of my talk. Now, the aim of this subject is to develop quantum version of these 2 devices, so computer as well as communication. So let's start with the computer part, and I will show you that why we are interested to build quantum computer. But nowadays we use desktop, laptop. I call them classical computer, because these computers are built by using classical information theory or classical electrodynamics, mechanical principles. Now, we know that they are useful in several fields. Education, business, to keep data in hospitals, in banking sectors, government offices, and possibly, especially since I'm talking in education institute, I must say that we realize even in this pandemic situations what is the importance of having computer and good communication devices. So these computers are helpful to write documents, to use internet, that means to connect each other, and so on. Now, at the same time, the computers are also useful to do mathematical calculations. So we know that in our classroom, usually we write a program in any language. It can be Fortran, it can be Mathematica, it can be MATLAB, other sophisticated languages, and we try to solve certain problems, mathematical problems. So so before I address some problems, let's just discuss that in classical computer, the basic unit is bit, so which is one of the 0 or 1. So usually we have some input in a computer, which we translate it into bits. That means we translate it into zeros and ones. Then the computer processes that bits to get the output, and this processing is done by performing certain logical gates, which we learn in our class. And then the computer gives us output in bits, which we can translate in any languages we want. So these are the basic 3 steps that the classical computer follow. And I will show you how we modify these things in quantum computing. Now let's choose the first problem that I want to address. The first problem is the prime identification problem. So the problem is the following, that I will give you a number and you have to tell me whether a number is prime or not. Now if I talk up to 100, so here the red circles are the prime numbers, and you know up to 100 probably even a school children, primary school children learn in their class. So what are the prime numbers? If you are more enthusiastic, then you can also find what are the prime numbers up to 1000. So these are all, previously it was a 2-digit number, now you have 3-digit number. So you can go on. So for example, I can give you a 10-digit number. I can ask you whether a number is prime or not. That means whether it has some divisibility other than 1 and itself. And you can find that this number which I have typed is actually not a prime number. It is divisible by 7. Now suppose I give you a now 10-digit number, you write a program and you find out whether it is prime or not. Similarly, I can give you a 100-digit number, you write a program and you can find whether the number is prime or not. And I go on increasing the number of digits. Now the question is, can we design a program which can solve any n-digit number? So n can be arbitrary. It can be 100, it can be 1000. And of course, we want to write a program which solves this problem in a reasonable time. I don't want to write a program which takes say years to solve. We want to solve in some reasonable time, and mathematically it is called a polynomial type. Although this problem looks so simple, but it was unsolved till 2002. When 3 Kanpur IIT faculty along with students, they solved this problem. They proposed an algorithm and show that this number is, this program can be done within polynomial time. So polynomial means, as you know, that if you have an n-digit number, then the program should take something order of n to the power alpha. So these were the 3 people. Actually the picture is old picture, around 2002 I guess. So this is a good news that we can solve this problem. So if we have a prime number, if someone gives me a number and I have to tell whether a number is prime or not, then there is an efficient algorithm which can solve this problem in a polynomial type. Now I question a second problem. This is a prime factorization problem. So the task is to find prime factors of a given integer. So here, for example, I have taken 45 and you know the prime factors of it. And so this is 5 and 2 3s. Similarly, if you have 72, then you also can factor it and you can find out what are the prime factors. And these are all 2-digit numbers. So we can easily do it. If I go on increasing the number of digits, for example, this is a 8-digit number. So then we need to think a bit more, but still it's possible because there are several 2 which are the prime factors and there are 17 which are also the prime factors of this number. So this is an 8-digit number. Can move to bit more. So if I want to say give you an integer which is an 80-digit number, so I want to find out prime factors of it. So the question is whether I give you an integer, typically what is the time it takes to solve. So what is the efficient algorithm that we can propose, which even a very powerful computer in the world can handle. And then we want to know that how much time it typically takes. Actually, if you have around 120-digit number and suppose you have something like 1600 powerful computers working, then to solve an arbitrary 120-digit number, if one writes an algorithm, then it takes around 8 months. And if you make 120-digit number to double, like 240-digit number, then again all these powerful computers can work, and typically it takes almost age of the universe. So this table shows that if you go on increasing the number of digits, then the classical computer, even the most powerful computers if you use in the world, then to solve this problem, you need a huge time. And this huge has to be quantified, and it's actually takes exponential number of steps. So to factor an n-digit number, the current algorithm, so the algorithm which are known till today in our computer, now this computer has been as powerful computer as we can build in today, takes exponentially n steps. If we are very precise, then it actually takes this number of steps. So till today there is no efficient classical algorithm which can solve this problem. However, it was shown in 1994 by Peter Shor, USA scientist, that if we use quantum mechanical principle, then this problem can be solved in a reasonable time. Again, the reasonable time means in polynomial time. So if we use quantum mechanics, then this problem can be solved in a polynomial time. So if we are able to build a computer which is built from the principles of quantum mechanics, then this can solve this prime factorization problem in polynomial time. So this is Peter Shor. So around this time of Peter Shor's algorithm until today, there are several algorithms are proposed. The notable ones are Grover algorithm, Deutsch algorithm. In all these algorithms, it was shown that if we use quantum mechanics, then that help to reduce the number of steps. So for example, certain tasks which can be solved in a classical computer, say by n steps, in all these algorithms it was shown that you require reduced number of steps. Like suppose it takes n steps, then it was shown that it can be solved by square root of n steps. Suppose it takes n step, it was shown that by using quantum mechanical principle, it takes 1 step, so on. But all these protocols, it was reduced polynomial number, but say n2 and the reduction is square root of n and so on. But in the Shor's algorithm, as I have told you, there is an exponential reduction. So if we can build a quantum computer, then we can achieve the word that already you have heard, quantum supremacy. So you can achieve that the quantum computer will be much more powerful than its classical counterparts. I will briefly talk about, quantum mechanics is the physics which describes about microscopic particles, so atomic or subatomic levels. And it was, as already mentioned, you have heard by the director, that it was formulated around 1900. Actually, the modern quantum mechanics that nowadays we learn in our textbooks around 1920s by several physicists, which include Einstein, Schrödinger, Heisenberg, Dirac, those from India, Raman, and of course, so it's important that it's atoms. So many important scientists here, Aditi, as well as all the experimentalists who help to make the shape of quantum mechanics that we learn now. So this is probably you have seen, many of you, that this is a Solvay conference in 1927 in Brussels, where most of the people, most of the scientists who helped to build or who shaped the quantum physics were present. Now, very briefly, if we want to describe some situations in a physical system, quantum mechanically, then we have to introduce vectors in a linear space where angle is defined. Now, a linear space in which an angle is defined is known as Hilbert space, and there can be a consideration of two-dimensional complex Hilbert space, and if we want to describe spin of an electron, that can be described by an element of a two-dimensional complex Hilbert space. And this actually gives us a basic unit in quantum computer. So as I have told you, in classical computer, the basic unit is bit. In quantum computer, basic unit is quantum bit. In short, it is qubit. What is qubit? It is a two-dimensional quantum state. So element in a Hilbert space is two-dimensional. That's why you say the two-dimensional quantum state. So mathematically it can be represented by like that. Here I have used spin degrees of freedom. So up and down is the up spin of say sigma z, and this is the down spin of sigma z eigenvector. Alpha, beta are complex numbers. Now you can also kind of get an analogy in geometrically. This you can represent this qubit. If you consider a sphere, then the poles represent the up and down spin, and the surface of the sphere, all the sphere represents a qubit. So the state that I have written here mathematically. Now, as you see that in classical world we only have kind of up and down, so the distinguishable object. But in quantum mechanics also tells us that there is a state exists which is a superposition. That means there is a state which is an up plus down. Alpha, beta can be anything, so there can be superpositions between up and down. So this superposition principle can be also talked about in terms of cats. So for example, in our world, in the classical world, we see that the cat is alive. At the same time, we see cat can be dead or sleeping. But quantum mechanics tells us that cat can be in a superposition of alive plus dead. So this is a basic thing of, one of the milestone of quantum mechanics, which helps to build quantum technologies. I think there is this next talk will be quantum mechanics primer by Indranil, and he will talk about more about this. I think about quantum mechanics, which I have just discussed. So just to tell you that the source algorithm that I have described, the success of source algorithm is based on the fact that it has used quantum mechanical principle. To detail that the quantum superposition principle actually helps to develop the source algorithm, or to develop the algorithm which can solve prime factorization problem in polynomial time. Now one can ask that whether this quantum computer is just a theoretical prediction. It's not. It has already been mentioned that there are several experiments going on, and already a small scale quantum computer has been built. So this is a timeline that European Union have proposed, where it was shown that there are several quantum technologies that they want to build over time, and possibly around 2035 they proposed we can have a universal quantum computer. As already you have heard that there are several technological giants like Google, IBM, Microsoft, Intel. There are many startup companies who have already built a small scale quantum computer. So as I have told you, the basic unit of quantum computer is qubit. So already many of you have heard that there is a 5-qubit quantum computer which is available in the cloud, and you can actually do a certain problem there, and you can see how it works. There are 16-qubit quantum computer which is also for use for common people, and also there are, as mentioned in this supremacy paper recently, where it was 53 qubit, and so up to now whatever quantum computer has been built in the world is a small scale one and up to 100 qubits. If you so there are say IBM 20 qubit, Google 72 qubit, and so on. So if you are interested, you can look at several websites which is available, and where you can get all these updates. I saw a very a lot of programs on quantum computation. So I saw that T.S. Mahesh from ISAT Pune will talk about quantum computations with nuclear magnetic resonance. Kanhaiya Pandey, who will from IIT Guwahati, will talk about quantum computations with ultra cold atom. Baladitya Suri from IISc will talk about quantum computations with superconducting qubit. Amit Kumar Pal from IIT Palakkad, he will talk about measurement-based quantum computation. One of the promising candidate now for building quantum computer. Prabha Mandam will talk about quantum error correction. So similar like classical error corrections, we also need quantum error corrections if you want to build quantum computers. So Prabha from IIT Chennai, she will talk about quantum error correction. So you will, in next 12 days, you will be able to hear a lot of talks on the quantum computer, and specifically also how to build quantum computer in physical systems. Here I just want to mention one thing. It's really revolution in technology. So as you know that if we build better and better candle or lantern, whatever nice way we can build, that technology is completely different than the bulb or LED bulb or electric bulb. So that was a technological revolution. So similarly, if we build a better and better classical computer, that will not lead to quantum computer, because the basic principle based on which we build classical computer is completely different than the one that we want to build, that is quantum computer. Because quantum computer which we are trying to build is will be a technology based on quantum mechanics, and so it is really a revolution in technology. Now I move to the communication devices, and I will talk about two types of communication devices. One is communication without security, another is secure communication. So I will start with communication protocols which doesn't security issue, which doesn't involve security issue. I will tell you in detail what do I mean by security. So as as we realized in this COVID pandemic situations, the importance of communication devices, we use several kinds, from our cell phone to many other devices and so on. So to connect our friends, to get information about our relatives, this webinar would have not been possible if we are not connected by internet. So this is also another example of good communication device. We see a revolution already in communication devices. So I say that I am probably from this era where we use, we write letters in a paper, send it via post. I have seen also typewriters people are writing, and the land phone, and even a dial-up phone we used to communicate, and also it was not available very easily. Already in 2020 we are now, everyone is now using laptop, mobile and other devices to connect each other. So this is already this technological revolution we have already seen. So now my idea is to tell you that if we want to build the version of this technology, this communication devices, what are the advantages that we will get? So what is the reason that we want to build quantum communication devices when we are quite happy with the communication devices that we use nowadays, because we are very connected with each other and so on. Any communication devices or any communication protocol should involve at least two people. But let's concentrate only on two people. So there is Alice and another one is Bob. Suppose Alice is in Ravangla and Bob is in Allahabad, and we want to communicate. Not together, they are situated in two distant locations. Now, for time being, I assume that Alice is a sender, receiver. It can be also called Alia or Garud, but from the classical cryptography protocol, which is very well developed, called sender as Alice and receiver as Bob. This can be any two celebrities, it can be between two teams, it can be between just two common people, it can be a sender and receiver. All these protocols, the main aim is to send information from Alice to Bob. So the aim is the sender wants to send some information. Now this information can be classical information or quantum. What do I mean by that? Now the classical information means that Alice wants to send some bits to Bob, or send some quantum state to Bob. Now this quantum state can be, for example, a qubit, a two-dimensional quantum state to Bob. So I have seen that in the program, Arun Kumarpati from HRI will talk about communication. I guess that he will be talking about communication without security, and the secure communications will be, this is a cryptography part, from H. Rahman from Presidency University. So I am sure that you will hear more about these technologies and the importance. But today I just want to give a flavor why we want to build communications without security or secure communication. So let's start with quantum state transmission. So we are interested that Alice wants to send a quantum state to Bob. Is a famous protocol given by the six scientists in 1993 and it's called quantum teleportation. Set, Alice wants to send some quantum state to Bob. It can be a qubit or it can be in a higher dimensional system, but let's concentrate on arbitrary qubit. So, two-dimensional quantum state, as I have told you. Now, suppose I don't have a quantum device, but I have only a classical device. Then, also we have written a chapter of a book edited by Dagmar Bush and Gerhard Leusch, and then also we introduce the entanglement theory. There are different, this bridge can have a different property than entanglement, can have different quantum correlations which are helpful to build quantum technology. As probably you will hear also a different perspective from Professor Arjun Majumdar's talk on quantum foundations and quantum information theory. So let's define at least briefly what is entanglement. So suppose Alice and Bob, there are two parties who are situated in two distant laboratories, say two distant places. And suppose these pink letters, they are complex numbers. These pink complex numbers are with Alice and the capital, the black ones are with Bob. As you see that this expressions can be written like that. So it's in a factored form, and this we call unentangled or the factorized state. Similarly, if I consider this expression where also the pink ones are with Alice and the capital letters of the black ones are with Bob, this expression can also be factored, and these are the factorized states. And if the bridge or the quantum teleportation protocol that I have described, if the bridge has these properties, then that bridge is not useful to send quantum state. So these kind of states, these factorized states are useless both for bridge to fulfill the task. On the other hand, if I create this kind of state, like here again the pink ones are with Alice, black ones are with Bob, and if the complex numbers are written in this way, then these are the entangled states. So the simple algebra when applied to certain vectors lead to these non-factorizable vectors or non-factorizable elements in the Hilbert space. Then we lead to entangled states which are useful as I have shown. Now this is kind of heuristically I defined. So as I told you that situation in a physical system can be described in quantum mechanics by vectors in a linear space with an angle defined. Actually that's the element of the Hilbert space. Now if I have two particles, two physical systems in quantum mechanics, then they are also elements of the Hilbert space, and then we have to actually write in a tensor product Hilbert space. We have to consider tensor product of the individual Hilbert space, which can be denoted by like that. So this is the complex Hilbert space at Alice's part. This is a complex Hilbert space at Bob's part. So for example, if we consider a solid, which can be represented by arrays of electron spin, and that means that it represents in quantum mechanics a tensor product of several Hilbert space, and that actually gives us the definition of entanglement. So suppose Alice prepares a state phi A in her lab and Bob prepares a state phi B in his lab, then the joint state looks like that. So unentangled or useless states are those states that Alice and Bob will be able to prepare even when they are situated in two distant locations. So mathematically useless or unentangled states are those states which can be written like that. An example of an unentangled states are like that. If I use spin degrees of freedom, for example. On the other hand, the useful states, that means the states which can be used for quantum teleportation, are the states which are called entangled states. And these entangled states are those states that Alice and Bob will not be able to prepare when they are situated in two distant locations. So then how will they create the bridge? Typically there is a source which creates the entangled state, and then source sends one particle to Alice, another particle to Bob, so that Alice and Bob share an entangled state or they have a quantum bridge. So this is a typical way to create an entangled state, and entangled state mathematically cannot be written in this factored form. And probably you will see in quantum mechanics class that this is a famous example of an entangled state, and this is the example of a singlet state. Now this is for pure states, the definition. Now you can generalize this definition for mixed states, but the definition and the notion remains same. So the useless or the separable or the mixed product states are those states that Alice and Bob can prepare even when they are not together or even when they are situated in two distant laboratories. They can do whatever quantum mechanical operations locally, and also they can communicate classically like a phone call. And entangled states are those states that Alice and Bob will not be able to prepare when they are situated in two distant laboratories. And as I have shown you, one of the preparation procedure, an example of an entangled state can be in mixed state scenario, which is a mixture of singlet and identity operator. Now this will be the situation in experiment, because in experiment pure states cannot be done. So we always have a noise which decoherent the entangled state, and for arbitrary state, although the definition can be easily given, but here I should stress that given a quantum mechanical state, it is not at all easy to detect, to find out whether a state is entangled or not. There are some detection methods available. There are many methods over the years available, but still it is, for arbitrary state, it is kind of missing. And as I said, that in experiment actually, the states will not be, states are in general not pure. They will be decoherent, they will be noisy, and so the robustness or how the decoherence affect the quantum technologies or the quantum information processing task, I think will be discussed by Sandeep Goel from ISA Mohali about the open quantum systems. Now, if you have although the detection is difficult, but if you have two spin-half particles, then it is possible to quantify entanglement. For example, there are entanglement measures which were proposed over time. These are the two prominent ones which can be computed. But I'm not going into detail of their measures, just to tell you that this exists. And as I have told you, that entanglement can be shown to be a resource state or an important ingredient for quantum teleportation. And like where we want to send quantum state from Alice to Bob. Now I will briefly tell you that even when we want to send classical information, then entanglement can help. Entanglement can give us some advantage. So I will talk about dense coding and cryptography. I think the theory of entanglement, here I briefly described about the two-party scenario where how to define entanglement. One can have an entanglement between several parties, when several quantum states are connected. Sorry. I think this entanglement theory will be covered by our Prabhu from IIT Harvard. So now I move to another scenario where I also talk about communication without security, but now the task is to send some classical information, and let's see whether quantum devices help or not. So, aim of Alice is the following, that Alice wants to send 2 bits of classical information to Bob. Hello, can you hear me? Is it okay? Hello?
Yes, madam. Yes, it's okay.
Okay, thank you. I cannot see you all, so it's very difficult to understand. Thank you. So Alice's aim is to send 2 bits of classical information to Bob. Now, to send these 2 bits, actually Alice requires 4 distinguishable objects if Alice has a classical device. So, for example, suppose I am a news reporter and I want to send the weather report of Ravangla to actually Ravangla, I put it as a sender. So a reporter wants to send the weather report of Ravangla to me, so to Allahabad. And also at the same time, he or she wants to send the PV Sindhu's badminton match report. So these are the 2 things. So let's see if I consider whether today is hot. I know that Ravangla is quite cold now, and I am thinking from Allahabad perspective, so I put it hot. So today is hot and Sindhu wins. This is one message, can be a possible messages I am talking about. Today is not hot and still Sindhu wins. Today is hot and Sindhu lose, and there is a possibility that today is not hot and Sindhu lose. So there are 4 possibilities if I consider that these 2 messages that Alice wants to send. Now we can use classical device. So the encoding can be like in the color of balls or color of flowers. It can be a very sophisticated thing, like a pattern of waves, kind of electric circuits, something. Any complicated way you can devise, but I will illustrate with a simple thing like a color of the ball. Whatever complicated way you use, you actually classically you require these 4 objects, 4 distinguishable objects. So for example, here I use the color blue, yellow, gray and green. So depending on the message, Alice encodes the message in one of the ball and then send this ball in a box, say, to Bob. Now since this color of the balls are distinguishable, then Bob can distinguish and can understand. So if Bob gets yellow, that today Bangla is cold, and Sidhu wins the match. If he gets grey, then the Bob knows that today Bangla is hot, and Sidhu lose the match. Sidhu was unable to win, and so on. So you see that clearly there are 4 colors of ball we require to send this 2 bit of classical information. And as I said, that you, whatever complicated way you choose, you actually require 4 dimension. 4 dimension means 4 distinguishable objects, 4 distinguishable colors, 4 distinguishable types of waves, frequency. It can be a laser, and it can have a different frequency, or it can have different bandwidth, whatever. I mean, many complicated way you can think of, but you require 4 distinguishable objects or 4 dimension. So, as I said, that encoding requires 4 distinguishable objects in classical devices if we want to send 2 bits of classical information. Now the question is, what about quantum device? If we have a quantum mechanical devices at hand, then whether we will get, we can encode in a smaller dimension or not? This is the question. So suppose again Alice and Bob a priori share this entangled state. That's a singlet state.
Ma'am, screen not visible. Excuse me, ma'am, my screen is not visible.
Is it?
It's visible.
Is it okay?
Yes, ma'am, it's visible.
Hello?
It's visible. Visible.
Yes, visible, ma'am.
Okay, okay.
It's working.
So maybe some people may have some connection problem. Okay. So I continue.
Yes.
So yeah. So suppose Alice and Bob share and this entangled state. Now to send 2 bits of classical information, actually Alice has to perform some unitary and then sends her particle of the entangled state, or the part of the particle, to Bob, so that Bob has both the states. Bob can perform measurement and can distinguish the states, and can decode these 2 bits of classical information. As you see that in the singlet state, actually it is a 2-dimensional at Alice's part, 2-dimension at Bob part. Because Alice's part has a possibility, it can be up or down. Bob's part also has a possibility up and down. So it has 2 dimensions. So Alice has 2 dimensions, Bob has 2 dimensions. And as you see that Alice performs unitary only on her 2-dimensional part, bits of classical information. After that, Alice sends her particle to Bob, and Bob measures and decodes the message and gets the information of 2 bits. So here, Alice requires only 2 dimensions to encode the 2 bits of classical information. That means 2 bits message that I have described. So you see that in classical device, you require 4 distinguishable objects of 4 dimensions. On the other hand, if Alice and Bob a priori share an entangled state, then to send 2 bits of classical information, Alice requires only 2 dimensions. So this protocol is known as quantum dense coding, because you encode 2 bits of classical information in 2 dimensions. So you densely encoded in a smaller dimension, and that's why it's called dense coding. It was introduced by Bennett and Weisner in 1992. This is a picture of Bennett. Actually, it was taken at HRI. Bennett visited us twice, and once he usually takes photographs. So one of the conference he was taking our photographs when one of our students has taken his photograph. So this is at HRI, he's taking the photograph of ours. The major steps in communications that I have described, probably you already understand, has 3 steps. One is encoding, which is Alice is doing. Then there is a sending part, which Alice has to send either via quantum channel or Alice has to communicate classically, as we have seen in case of teleportation. That is the classical communication. And in case of dense coding, Alice has to send quantum state to Bob, so has to use quantum channel. And finally, Bob has to decode. Now, this encoding of sender can be, as I have already told you, so information, as Landau said, that information is physical. So information must be encoded in or decoded from a physical system. Now in the classical world, we have seen that the encoding and decoding can be done by the classical systems or the classical skates. So it can be color of bulbs, charge of particles, wave pattern, and so on. But they all will be distinguishable, and that's why they call mathematically orthogonal states. On the other hand, in quantum world, there are states which are non-orthogonal. There are states also to be orthogonal. So in quantum world, we have both orthogonal, that means distinguishable, as well as indistinguishable states. So both orthogonal and non-orthogonal states. And so possibly we are getting advantage. So as I said, that Alice has to encode, then sends via some medium, can be nowadays by optical fiber, in old days maybe via some horse-ridden person, and then Alice sends her part, or Alice sends her message to Bob, and Bob's task is to decode. So these are the 3 major states that any communication protocol should follow. Now, as I have tried to establish that this encoding, sending and decoding, if we use quantum mechanics, then whether it helps us to enhance the capability of sending information. And as I have told you, this information can be both classical, that means can be written in bits or in qubits. And as I have probably tried to convince you, that if we use quantum mechanics, specifically if we use quantum mechanical state like entangled state, then we can enhance our capability of sending classical information as well as quantum state. So this was the reason to build probably quantum devices in communication protocol. Now here I should tell you that up to now I have talked about only point-to-point communication, like there is one sender and one receiver. But this has a very limited usefulness that we probably understand from this webinar, because in webinar we all are situated in distant locations and somehow we all are connected. So there are many senders and many receiver is the kind of network that we want to build. So this is actually a flight network from Air India. So whether we talk about classical information transmission or quantum state transmission, we want to involve, or we want to develop certain protocols or certain devices which involve several senders and several receivers. So for examples, we can have several senders, then there is the single receiver, and if we talk about classical information transmission protocol, they are connected via certain channels, so they are connected via internal state, and then we want to send information from sender side to the receiver. And this question is not so easy, And there are certain, we have actually in our group, we have addressed this question and we try to solve this. So for example, if we talk about classical information transmission, we can think that the senders and receivers, they share an entangled states. Encoding can be done in some way. It can be locally can be done, and then receivers also decode the message via local operations, and they can classically communicate, but they cannot do global operation. So because they are situated in distant location, and the sending from sender to receiver side can be through a noiseless channel or can be a noisy channel. This problem is well set, but there are several open questions, and we still don't know in full generality how to establish this in a quantum by using quantum mechanics. So we are working extensively at HRI in this problem and trying to solve certain things, both theoretically as a theoretical physicist. So there is another network that we can talk about where we want to share entanglement over large distance. And for example, we can have a one-dimensional quantum network where some pre-decided node like 1, 2, 3, 4, the yellow nodes wants to share certain entangled states. And we recently have proposed that by performing certain measurements on these red nodes, one can share and detect entangled states between 1, 2, 3, 4. Then we go on to two-dimensional quantum network and so on, but there are several open questions that still remain unanswerable, and we are not able to answer. It's much more difficult question. Probably some of the questions you will learn in the entanglement theory theory lectures and so on. If you're interested, you can look at some of our recent works which are available. Up to now, communication protocols I have described only theoretically, so the question remains whether it's only theory. So let's talk very briefly about experimental progress. So one of the potential candidates to do quantum communication protocol is by photon. People use two types of polarization degrees of freedom to represent a qubit. So right-handed and left-handed circular polarization are used for qubit, and these polarization degrees of freedom can be used to create entangled state. So again, there is a very nice RMP, Reviews of Modern Physics paper, where you can learn about photonic entangled states, and this is a schematic diagram how to create an entangled state by using this photonic system. And actually this is also to tell that there is an entangled state created. I'm not going into detail. Now there is an experiment in photons. For example, there is between two islands where the teleportation experiments were done. These two islands are near in Africa, and this La Palma and Tenerife, they are 143 kilometers away, and there was a teleportation experiment there by Vienna group and Tanzania group. So it just tells us that there are two cities, for example, Varanasi and Allahabad, can be connected via entangled states. But there is a breakthrough experiment in 2017 in a Chinese group led by Han, where they use a satellite based communication protocol where they are able to connect or they are able to share an entangled state between 1200 kilometers away, two cities. And this is a very nice experiment, and they use photon. So now it's possible to connect even Kolkata Guwahati, for example, which is kind of 1,000 kilometers away. And of course, say Kolkata Rabangla is possible. Maybe Rabangla and Hawaz is a bit far, but quite possible to connect via entanglement states. And we can perform quantum teleportations between Rabangla and Allahabad. Another potential candidate for both quantum computations and quantum communication is ion trap, where the internal levels of ions was a qubit. And recent experiment of quantum computers that was reported, 11 qubit quantum computer. Here they used certain ion they connect 11 qubit fully connected quantum computer. And now in quantum computer, just like a classical computer, we also require some quantum gates to be performed, so we have an input like classical computer. We have now a quantum computer where you perform some quantum gates which manipulate the input, and finally we get the output. So they have shown a very high fidelity quantum gate implementation. It was shown that if you want to beat the quantum computer, it is enough to have a single qubit and 2 qubit gates. And they have shown both the gate implementations with very high fidelity. There are other systems which are also potential candidates for building quantum computer. Alta-core atoms in optical lattices, which also you will hear from Kanaiya. Nuclear magnetic resonance, which you will hear from T.S. Mahesh. There is also semiconductor devices, and of course there are superconducting qubit, which actually have this 5 qubit superconducting qubit, the small scale quantum computer, 16 qubit quantum supremacy test, all are done by using superconducting qubit, which you will also hear from Baladitto's talk. Here I just want to mention a very recent paper last month where the group led by Pan, who has done this photonic experiment, they actually demonstrate a superconducting quantum processor. They showed that they can have a Majorana zero modes, they map that thing. And they said that can be used to perform even a quantum communication or quantum teleportation protocol in superconducting circuit, and this is their actually the schematic diagram how to implement teleportation in superconducting qubit. Now here I must say that photonic qubits are used to do quantum communication protocol over long distance, but if we want to build a quantum computer, we also need small distance transfer of quantum states or classical information, which can be a smaller distance, where the superconducting qubit and now also ion trap. There are several experiments on quantum teleportations, which are so they are the potential candidates to implement quantum communication protocol in small distance. So as I have described, and as you will hear in next 12 days, finding physical systems where quantum computer can be built is one of the important question in this field. Finding physical system where quantum communication can be realized, this is another important question. Both will be talked about. And finding, say, useful systems where entangled states can be found, so that you can use these states for quantum communication protocol or, say, measurement-based quantum computation. So both for quantum computation, to build quantum computer as well as quantum communication devices, entangled states can be a useful resource. So this is another important question that addressed in this field, and I think this will, Ujjwal Sen from HRI, he will talk about, he will address this question, so he will try to show you that many-body physics or many-body systems can be a useful resource, to generate entangled state, to generate to build quantum devices like communication or computational purpose. Some of the works we also work extensively in this direction. Some of our recent works, if you want to look, you can look. We also have a review article which actually addresses this question, like how one can use quantum many-body systems. So if you are interested, you can look and you can get a recent progress. So finally, I move to the last part of my talk, and I will talk about quantum version of secure communication. So this part I think will be covered by Ramich, quantum cryptography. So I will just briefly describe what is the aim of quantum secure communication. So in these protocols, Alice's aim is to send certain classical information securely. So again, we have two people, Alice and Bob, but now there is an eavesdropper. So Alice wants to encode information in such a way that the third party will not be able to gather information. So only Bob will be able to get the information. No other third party can get the information. So Alice's encoding has to be done in that way. On the other hand, eavesdropper who wants to gather information from Alice to Bob, eavesdropper aims to gather as much information as possible that is flowing from Alice to Bob. So so you can think that the eavesdropper can have all the power. So eavesdropper can have quantum computer. Eavesdropper can be thought of as a suprema, has all the power. So Alice's power in some sense restricted, but Alice can use any thing. So, but Alice, anything which is available in the world. On the other hand, you can think that the quantum or the eavesdropper can have a power which is with the inverted comma like a god. So Alice has to encode information in such a way that eavesdropper will not be able to gather information what Alice is sending to Bob. So this is in 2020 probably way we can think of. Now again probably we always come back to this pandemic situation because we are kind of now last 6 months we have to deal with this. So probably we understand the usefulness. I mean, I think everybody in this who is listening, you all are convinced the usefulness of secure communication. We use internet banking where we only want to send or want to communicate with the bank, and we don't want that any third party can gather our password or can use our account. And we every day, whenever we on the mobile, we heard about the fraud, etc. So we understand the security of, for example, internet banking. We know when we use debit card for internet purchase, say marketing, there also it's we have to go to secure options where we get OTP so that we can transfer the money to only to, say, for example, Amazon or Flipkart, but not to other people. So, and it's also useful in national security. And that probably people understand from ancient time because the two parties wants to send information securely. So that's also important. Now, as I have already told you that the classical cryptography system that we nowadays use, for example, in internet banking or in other purposes, so to check our now for example, the results of say in 10 standard, 12 standards, IITs, etc., all through some logging. So these are all secure based communication. So we are very happy that most of the situations that are quite secure. But so classical cryptographic systems are very good, very useful. But the security of this classical cryptography system is based on the fact or the belief that some mathematical problems cannot be solved in a classical computer in polynomial time. As I have described, for example, the prime factorization problem. So we know that the prime factorization problem cannot be solved in a classical computer in polynomial time. So the security of the classical cryptography system is based on such such mathematical problems. So as I have told you that since these mathematical problems can be solved using quantum mechanics, like the prime factorizations can be solved by Shor's algorithm. So if we are able to build quantum computer, then all current crypto systems become insecure. So all the internet banking, all the things that we based on which our classical crypto system are based on, if anyone can build a quantum computer, they can hack. They can just make all these things insecure. So what to do? Now the remedy again comes from the quantum mechanics, because we can now build a quantum cryptography system. So we can now develop a cryptographic protocol whose security will be based on the validity of quantum mechanics. And we believe, I think in this room, that we all believe that the quantum mechanics is valid. And that important point is that this cryptography protocol based on quantum mechanics remains secure even when we have a quantum computer. So we can prove that if we can build a cryptographic protocol based on quantum mechanics, then that quantum cryptography protocols remain secure even when we have a quantum computer. So even when eavesdropper has a quantum computer or anyone has a quantum computer, still it remains secure. And there are protocols which were proposed. The two main protocols are the Bennett-Grashof 1984 protocol and Arthur Akers 1991 cryptography protocol. Now here, to generate a quantum key, sends a sequence of randomly generated quantum state to a receiver. The point is that if eavesdropper intercepts or eavesdropper wants to gather information about the key, then the laws of quantum mechanics ensure that eavesdropper cannot do this without disturbing it. Now if eavesdropper can disturb the state, Bob and Alice can understand that someone is in the channel, and so they can disturb the protocol. And this is good because the presence of eavesdropper can be detected by using quantum mechanics, and this was actually based on the fact of no cloning theorem, which tells us that we cannot clone arbitrary quantum states, or we cannot copy, we cannot have a quantum Xerox machine. Also the fact that if you disturb quantum states, then one can detect. So if when Alice is sending some information to Bob, if there is an eavesdropper, if eavesdropper wants to gather information, eavesdropper has to disturb the state, and that disturbance can be detected by Alice and Bob. This is actually Bennett, Grashof and Eckert they are discussing in one of the conference. Again, the question is whether it is only theory. It is not, because I think quantum cryptography machines are even available. If you search in Google, you will find small devices. This was several companies which sell quantum cryptography devices. So, for example, And there is a Football World Cup at South Africa where there is a quantum stadium project where they use quantum methods to encrypt, to ensure some security between stadium and the joint operations center. And this was done quite years back, and also there is a Geneva elections where people have used. But over the time, there are several companies, even many startup companies have come up with cryptographic machines where these random quantum states are used to generate, and they have shown that what are the eavesdropper, how powerful eavesdropper can be, so that this can be tracked and so on. So there are several quantum cryptographic experiments going on over the, in the world. So these are experiments that I talked about are done led by Nicolas Gizon and his team. Here I just want to mention we also worked on the security issues of quantum cryptography. So we proved recently our complementary relations, which provides a bound on the secret key bit on a quantum key distribution protocol. We also worked extensively on monogamy of quantum correlation measure. Now, monogamy tells us that if Alice and Bob share an entangled state, then Alice and Bob cannot have any entanglement with the eavesdropper. Now, if Alice and Bob share a maximally entangled state, then Eve cannot have any entanglement, or Eve cannot have any quantum correlation with Alice and Bob. However, if Alice and Bob has a non-maximally entangled state or noisy state, then Eve can have some correlations with Alice and Bob. So there is a trade-off between Alice-Bob correlations and Alice-Eve or B-Eve correlation, and that is called monogamy of quantum correlation. And in the R2 record quantum cryptography protocol, which is based on entangled state, this plays an important role. And now we know that these R2 record entanglement based protocols are important to achieve device independent security. And so this monogamy of quantum correlation also play an important role in to obtain security. And we have written a book chapter of monogamy of quantum correlations. If you are interested, you can look. Finally, I just want to mention some of our recent results, which actually known as no masking theorem, which tells us that masking of quantum information is not possible. Now, if quantum information is hidden from subsystem and spread over quantum correlation, then this is called masking of quantum information. Now, if I replace quantum by a classical information, then this is possible. That means masking of classical information is possible. Classical informations can be hidden from subsystem and spread over quantum correlation. But what we have shown recently that in case of arbitrary quantum information, then this masking of quantum information is not possible. And this has implications in quantum cryptography. So with this, actually, I come to the end of my talk. So I hope that I am able to convey the message or to convince you. As already mentioned in the introductions by the director and Amingo, that quantum mechanics can revolutionize our power or capabilities in terms of computation as well as communication. Now, these communication capabilities can be with or without security. In both the scenarios, I have told you that quantum mechanics can help quantum mechanics can give us or can guarantee security in communication protocols. So, as I have told you, in 2018 onwards, we have seen several quantum cryptography experiments. It's already in reality. And so quantum cryptography machines are already a reality. We probably look for quantum internet where we want to connect several senders and several receivers. And as I have mentioned, there are some works also from our group and around the world. But still there are several open questions, both theoretically and experimentally. So people over the world are trying hard to establish this quantum communications for which can connect several centers and several receivers. So we hope that it will be soon be a reality in over maybe 5 years. And I also have told you that small scale quantum computer is already a reality. So less than 100 qubit quantum computer is already by several groups have reported, and they have shown certain tasks which can be done by using quantum computer. But really to show the quantum supremacy, we need more than 100 qubits, and I think this is an experimental challenge. Also, how to really address the questions of decoherence and so on. And both theoretical and experimental works are going on to address that. Here I haven't mentioned several quantum technologies which are important. For example, in quantum metrology, we have seen there are quantum sensors which people have built. There is quantum battery where we can store energy, and it can be shown that the quantum mechanics help to store energy. So there are quantum thermodynamical machines which has been developed over the years, and it has been shown that quantum mechanics help to perform certain thermodynamical, can enhance certain thermodynamical capabilities. There are other quantum technologies which are developed, and I am sure there will be much more new technologies which will come up. And with this, this is a group at HRI. Some of the work I have mentioned have been done by people. Some of them have left. Some of them have also joined. So here actually we can see 4 speakers who will be talking. So Arun Kumarpati from HRI, Ujjwal also from HRI, Prabhu from IIT Bharwar, and Amit who were in IIT Palakkad. So this photo was taken during a conference at HRI in 2018. So they are our past member. Anindo is also a past member at HRI. I am very proud that today he has organized and invited me. I have 15 PhD students, 5 postdocs, and 3 faculty members, and I think all of them will be talking in this workshop. So thank you very much for your attention, and if you have any questions, queries, also please write to me. You can find my email, and if you are interested when the pandemic will be over, you are also welcome to visit HRI.
Thank you very much, Aditi. So there are some questions in the chat box. Would you like to take it yourself, or should I read them out, some of them?
Yeah, it will be good if you can read them out. Then I can share. I can go to the share screen, because if I go to the share screen, I will not be able to. So is it possible for you, or I can do it?
Yeah, I can do that.
Okay, thank you.
So the first question is partially entangled state useful for quantum communication, or should we use EPR states only?
No, it's useful, and actually that's important, because in experiment you usually have a noisy state, as I have already mentioned. So that means the entangled states are not fully entangled or maximally entangled. It will be partially entangled. And all the experiments that I have talked about, whether the teleportations via satellite, teleportations over 2 distant islands, all they are not the EPR states. They are something which are actually noisy states, which are non-maximally entangled states. And we see that they can successfully do this teleportation experiment, and so they can well perform quantum communication protocol, and that is the one which is a challenge. We have to develop quantum internet where all the systems are noisy, all the channels are all noisy. still we should get advantage over the classical counterparts. That's the challenge.
So the next question is, what does the assertion information is physical intuitively mean?
Physical in the sense, I think if I understand correctly, so the point is that whatever way you want to import information, that should be in a physical system, as I have said, either encoding or decoding, whatever you think. So in the classical protocols, you can think of a bandwidth, frequency of a laser, as I said, wave patterns can be different, so some distinguishable objects, or if in a simple way you can think of the colors of the ball or colors of the flowers, that can be also be used to encode information. The point is that in case of quantum mechanics, we know there are states which is not available in the classical world. Because I told you that there is a quantum superposition principle, so there are states which you cannot see in our classical domain. So those states can be used, and actually it was shown that those states can be used to enhance the capabilities in communication protocol.
Thank you, Aditi. So we have a few more questions. Will the number of layers or elements in OSI model for communication network decrease in quantum communication? So he's talking about some model. Yeah.
Sorry?
So the
Yeah.
I'll repeat,
Yeah, I probably understand. Look, I mean, these things are under research, because I understand there will be a layers, right, which you are saying. So I just gave a flavor of how quantum mechanics help to give the advantage in the communication domain. Of course, there are several complications. So if we really want to develop quantum communication protocol, then that also will somehow has to tag with the classical communication protocol. Both actually kind of, so there are several layers which has to be actually, still people don't know. So the researchers are trying hard how to.
Can I just add to this?
Yes, sure.
Yeah, this classification of layer is basically based on the functionalities, nothing to do with your more of the quantum computing. So that is sometimes the layered architecture of various services or various devices. So quantum computing, I believe, is more of a computational power rather than the services at different level you provide. So you can even measure, because it's TCP/IP has a 4-layer only. While OSI model in network that is 7-layer.
Okay.
So it does not matter whether the layers are reduced or not, but more or less they are being divided based on the functionality. So
I don't. I am sure that the electronics people know much better.
Yes.
Answer. I can completely understand.
That's why I thought I should.
Thank you.
They should not.
Yeah, thank you. But recently, I actually have a panel discussion with IEEE, where I was talking with some people, and there I also came to know that, for example, in Japan and these people, whether they have the communication, the electronics people, so they were telling me that there are several layers which actually somehow they tag with the quantum communication devices, and there will be a processing with the classical communication devices. So together they will get, but this is under research, so we don't know really how we will be able to solve the purpose. This is under the project called Quantum Internet, which you can see in European Union have declared, USA have declared, China have declared, now India also have declared. This is under the people who are under the study that how this can be realized.
Thank you, Aditi. The next question is, can quantum cryptography be combined with secret sharing schemes?
Yeah, I mean, quantum cryptography and secret sharing is just, I mean, quantum secret sharing involve many parties. Cryptography that I have described is just between two parties. So both are kind of, the security will be much more complicated when more parties are involved, as one can imagine from our common sense. And there are some people who address that question, and for example, in our group we have some work, but it's much more complicated to address. As I said in my talk, since Alinda said it's a overview talk, so I just have mentioned, I try to give the flavor why we want to really build quantum technology. I haven't gone to the detail. There are several questions which one can answer, one can try to address, and several questions are answered. Probably you will hear when the specific topics will be addressed by the later speakers in this debate.
There is another question on cryptography. Can elliptic curve be used in quantum cryptography?
This is a good question, but I think I have not, I mean, yeah, that is another way, because we know that in classical cryptography, people use this elliptic curve thing. So I think I have seen some papers, but yeah, I mean, that is, I mean, one has to use some quantum mechanical action. So I think this is not yet, I mean, at least as far as I know, one has to look for more.
So the next question is, will the increment of bits increase the computational load, or is there any limitation of increasing bits? I mean, qubits maybe.
Yeah, actually it has to increase the nodes if you want to increase the bits, but whether you want to use several times a single channel, how to do, I mean, these are the much more complicated technologies that we are talking, but yes, I mean, in some sense nodes can be increased. For example, the jail storing protocol that I have described, where the qubits are used to encode classical bits, we know that if we increase nodes, we can send more number of bits.
Okay. So what is the status in India of developing the quantum computer, or up to how many qubits are we targeting?
Yeah, so as many of you know, Department of Science and Technology has first initiated the mission mode thing called Quest, Quantum Enabled Technologies. And there we all have the projects, so both theoreticians and experimentalists, we are working together. There are several other initiatives, like I think in January or February, Prime Minister has declared this 8,000 crores investment on quantum technologies. And that proposal, as far as I know, they are people are trying to build. So today there is also, there is one component of this Vaibhav summit which is going on, which was inaugurated on 2nd October. That also have a quantum technology part, and today there will be the first session on quantum technology. I mean, today from 6:30, we are also, I am kind of part of that. And there will be several discussions. Anybody interested can join. There will be NRI people who will be joining. So, for example, on 7th, I will be coordinating a sessions called Atoms and Sources. There are quantum communication components. There are quantum communication components. So, anybody can attend that. One has to register. Probably everybody who are in the institute have got that link of the Web Summit. So there are several developments going on in India. I must say that over 20-30 years, I mean, we have started this HRI group around 2009. It's quite new, 12 years. But there are several people who are working in quantum information and computation, specifically on theoretical part for a long time. It is a big history in India. And the experimental parts are also going on. Several people are who are doing in photonic devices, superconducting qubits, ion trap. So there are several in Quest, this DSC program. There are several groups have been built who talk about, say, nuclear magnetic resonance, which you will hear from Mahesh, superconducting qubits and traps, cold atoms, and this. So there are several groups have been built in Quest. And I think that this 8,000 crore, when the proposals will be formed, new projects will come. And another good part which is coming up is with the companies. Now the private sectors are also kind of involving themselves in building. So as you know, the IBM have started this KISS kit, which actually has some seminar series going on over the world. But they have taken some initiative also in India. So people are speaking on there, and they have several programs. IBM India have started some kind of collaboration. Also, they are talking with people. So they have called some meetings, something in August, I guess. I don't exactly remember that during this pandemic. There are IEEE last week has some panel discussions. IEEE India has done some satellite meeting. So there are several activity going on, and I'm hopeful that we will be reporting something also experimentally soon.
Another question is, what about the storage of qubits?
That's a difficult part actually. That talked about quantum memory, and that's a difficult, because that probably will be addressed by Sandeep in the open quantum system. So that's a main trouble, because to keep the quantumness, or to keep us even a single system or more systems in a storage device which can keep the quantum characteristics as it is a difficult part. And many people are working on that directions, have some progress, and that's why probably this quantum proliferations over 1200 kilometers are able to do some experiment. But quantum memory is a difficult part. People are addressing theoretically also. It's a difficult question to know, so but people are in progress.
If we are end with this question, what's your view on nitrogen vacancy effects in the nucleus as a use for qubit storage devices?
Yeah, I think nitrogen vacancy center are good for quantum sensors as well, but I think over the world the experiments are just coming up, so so we are still not sure about the deterrence and etc. But I think maybe within a year or so it will be more and more clear. Also, I must say that nitrogen vacancy center, there are experiments going on in India also, so we hope to learn more.
Thank you very much, Aditi. Thank you for.
Thank you. Thank you. Okay, so I will end the session on it.
Yes, thank you, sir.
Bye.